guys. So it looks like most of you have either set this up or gotten an answer, and from what I saw, the answers that I saw looked good. So just to quickly go through it for the sake of the recording, all we're doing is using our general formula that our K sub C is our products, concentration of our products to the coefficient. If we have more than one product, this time we only have one, so I'm just gonna, oops, over the reactants. So it looks like everyone had this set up correctly, so we had 0.03 squared over 0.81 times 0.75, and that gave us something like 1.48 times, or 49, whatever, times 10 to the negative third. Technically, we only have two significant digits, so it would be 1.5 times 10 to the negative third. Because we have that 0 after 3 is important. That tells us we have two significant digits there. All right, and then because our Kc is significantly less than 1, that means what is the composition of the reaction mixture? Mostly reactants or mostly products? Yeah, Roger? Yeah. Or we could also say that the equilibrium is, yep, to the left. Okay, good. That is, I would say, 25% of any equilibrium questions you might get on the test would be, being able to set up and calculate the equilibrium constant and be able to say whether it's going towards the reactants or towards the products. Yes? That is a good question. You want to pull out your data booklet and look at the first couple pages? I think you have to memorize it, but I could be wrong. Okay. 7. Okay. All right, so yesterday we started talking about how to manipulate the equilibrium constant if we change certain things. For example, we talked about how if we reverse the equation, then we get the inverse or reciprocal of Kc of the forward reaction. So we looked at this example of H2 plus I2 yielding to HI, the one we've been kind of using this whole time, reversibly yielding to HI. We're given a Kc at a particular temperature. If we look at the reverse reaction, the Kc for that reaction at that temperature, remember that temperature matters, is going to be 1 over that. So this is essentially 1 over 794. So here I have something that we'll be talking a little bit more about later, possibly today, definitely tomorrow if we don't finish it today. This is called the Haber process. This is the production of ammonia. It's one of the most important chemical reactions in the history of chemistry because it allows us to take the abundant nitrogen out of the air and fix it into something that we can actually use. And Haber, his name is on it because he was the one who figured out how to do this more efficiently so that it actually didn't take ridiculous amounts of energy. And he used the principles of equilibrium to do that. So this is N2 plus 3H2 gives us 2NH3, all gases, and our Kc is 9.60 at 573 Kelvin. So what would the Kc be of the reverse reaction at 573 Kelvin? How would we find that? Yeah. It would just be 1 over 9.60. Oops, it's not 90. Okay. So whatever that is, I mean, you don't need to calculate it out as long as you know how to do that. Okay. All right, I kind of rushed through this at the end, so I wanted to go over it again. If we change the coefficients in the equation, then we change the basically an exponent of Kc. We take Kc to a particular power. So if right now, with this reaction written the way it is, H2 plus I2 gives us 2HI, and we have an equilibrium constant of Kc for that reaction at a particular temperature, then if we double the coefficients of that, then we're going to square the original Kc. And if we have those, then we're going to take the square root, or take it to that 1/2 power. So whatever we do to the coefficients becomes the exponent of Kc to calculate the new Kc. This is definitely in your study guide, and of course I didn't put the page on here. Oh, I guess it just has the table. So what you should be doing right now is filling out, as we go along, this table that is on page 10. So far we've looked at reversing the reaction. So we talked about how reversing the reaction changes Kc to 1/Kc. We talked about how doubling the coefficients gives us our original Kc squared. How halving the reaction coefficients gives us the square root of the original Kc, or Kc to the 1/2 power, whatever. And you can, I'm not going to worry too much on the effect on the equilibrium expression. You can go through and think about how you would write this out, write out the equation for Kc under these different circumstances. Obviously, well, we'll just go through it. So we would flip it. If we reverse the reaction, the old reactants would become the new products, and vice versa. Doubling the reaction coefficients would be making each of these parts of the equation multiplied by 2. So that's where we get the squaring from, because little a is the coefficient for substance A, and we'd be just squaring that, and the same thing with halving. And the last thing that you need to know is if we have a series of reversible steps that constitute a larger chemical equation, and we're talking about going from step A to the end, and we're looking for an equilibrium constant, an overall equilibrium constant for all of the steps, and they're all reversible, then you are multiplying each one. So there'll be each step will have its own reactants and products, and will have its own Kc, and you'll multiply those together to get the overall. Yeah. So and so on. So however many steps we have, just I'm not going to write out that whole thing. So if we look at the exercise right below here, we're given Kc for this reaction. This is the decomposition of hydroiodic acid, written backwards from the way we've been writing it. But this is the reaction as given, so we're now considering this the reactant and these the products. Now we need to figure out the equilibrium constant for this reaction. Again, notice it says at the same temperature because that matters. So basically, what have we done to this reaction to get here? Yeah. Yeah. You multiply the Kcs. Just the Kcs, yeah. Yeah. I mean, it does end up essentially being that, but yeah, so I don't really think I don't like the effect on equilibrium expression here because the equilibrium expression of each step is going to be the same. You're just multiplying them all together. Yeah. Yeah. No, it should not matter. It shouldn't matter. Well, okay, yes. So you would, if you're adding reactions, you would change whatever else you needed to change first. So if you did something with the coefficients or flipped it, you would do that first before you multiplied the reactions together. But as far as flipping it or squaring it or square rooting it, that shouldn't matter. It's a good question. So what's the difference between the first reaction and the second reaction? What have we done to it? Yeah, Nick. Okay, good. So we've reversed it and we've halved it. We've halved the coefficients. Right. Right, exactly. So we take our 0.04, 1 over that, and then we are does it matter? It doesn't. It should. Right. Before or after, right. Hang on. Let me see what he does in the... What? Sure. Sure, go ahead and do that while I... Oh, he doesn't actually go through it. Would it be... It's the same, yeah, okay. That's what I thought it shouldn't matter, but I hadn't actually done this one, so yeah. So it doesn't really matter if we square root the whole thing. I guess because the square root of 1 is 1, so it still ends up being the same thing. If this, and I guess because it's the reciprocal, the numerator will always be 1. Yeah, it doesn't matter. So what'd you get, Roger? Okay. That's right. Yep. Yeah, Devin. Well, the reciprocal is always going to be 1. 1 over that. Yeah, so it's not going to matter. Yeah. Yeah, I was trying to work that out in my head. So thank you, Roger, thank you, Nick, for asking it, Roger for figuring it out. The order of operations doesn't matter. Again, if one of the multiple things you're doing is adding together 2 reactions, then get your Kc for each one separately and then multiply them together at the end. Okay, so the Kc is, and let's see, we are now, I believe, on the next page. Yeah, on page 11 in your study guide. So K is our equilibrium constant. That gives us the relationship between reactants and products at equilibrium. But what if we're measuring concentrations of our reactants and products at a time other than equilibrium? How do we calculate that, and what can it tell us? So that gives us what we call the reaction quotient. So it's calculated exactly the same as Kc. QC is exactly the same. It's the concentration of products to their coefficients over the concentration of reactants to their coefficients. The only difference is this is calculated from the concentrations at any point other than at equilibrium. Yes? No, a specific point. Yep. So you'll be given that information. It'll say it'll say something like Kc is X, and here are the concentrations at this point of the reaction. Where is the reaction going from here? Okay? So, at equilibrium, QC and Kc are exactly the same because it's at equilibrium and the concentrations aren't changing. They're constant. If QC is below Kc, if it's less than Kc, then we're going to be moving the reaction to the right towards the products in order to make QC, in order to increase the value of QC. Okay, because remember the products are on top of our expression. So if QC is less than Kc, the reaction is going to trend towards the right from that point in order to get to equilibrium. So we're going to make more products until we reach equilibrium. If QC is bigger than Kc, then the reaction is going to go to the left. We're going to start making more reactants so that we can get to the equilibrium where our concentrations are constant. So you may be given a K, given the means to calculate Q, and asked, what direction is this reaction going to? The left or the right? Or towards the products or towards the reactants? So just like when we have a low Kc, we have mostly reactants at equilibrium. If we have a low QC, we have a lot more reactants than we have products. And we're going to push the reaction in the product direction and vice versa. It's not exactly the same thing because the Kc is telling us the composition at equilibrium, but it's the same basic idea. All right, so here's an example. So we have this reaction, CO2 plus H2O reversibly yields H2 and CO, carbon monoxide and water reversibly yields hydrogen gas and carbon dioxide gas. The Kc is 5.10 at this temperature. At a certain point of time in the reaction, the value of Q is 4.10. So which way will the reaction proceed? Will it proceed to the left towards the reactants or to the right towards the products? It'll be to the right because our Q is less than K. Reaction is going to proceed to the right, to the product side. Okay. So it'll depend, and I'll give you some examples of test bank questions. There are only, in the whole test bank, there are only 14 multiple choice questions that are on kinetics. So it usually gets pulled into, equilibrium. It usually gets pulled into the paper 2 questions. Which brings us to So all of this stuff is really maybe like, all the stuff we've done so far is maybe like 30% of the questions on the exam that would be about equilibrium. The rest of them are dealing with this next subject, which is Le Chatelier's principle. So if you took honors chem last year, you may remember this. We talked about it a little bit. We did not learn it 2 years ago. We ran out of time with COVID. So the idea is that if we have a system at equilibrium and something changes, then the reaction is going to shift to get back to a new equilibrium. It's not necessarily going to get back to, in fact, it generally won't get back to the same equilibrium because it's got different conditions, a different temperature, different concentrations, whatever. And this is basically the concept of homeostasis in biology, right? That, or a thermostat in your house. If the temperature gets too high, the AC will kick on until the temperature lowers. Same thing with your body temperature, right? On a hot day, if you go outside and you're at track practice, your body temperature is going to rise, you're going to sweat. The sweat is going to cool your body down. It's not going to cool your body down to the level of body temperature that you're at right now, right? You're still going to feel hot, but you will be within the realm of like reasonable body temperatures where biochemical reactions can take place. I mean, maybe not in the last few days. You haven't been hot and sweaty, but eventually. Okay, so that's the idea, is that if we disturb the equilibrium, things are going to shift in such a way as to minimize that disruption. So the changes that we can make to a reaction at equilibrium, the ones that you're required to know about and know how it affects the equilibrium, are change in concentrations of reactants or products, and that's going to have different effects on the equilibrium, whether it's a reactant or a product. Changes to pressure of a system that involves gases. Not everything has to be a gas in order for pressure to matter, but some part of the reaction, either one of the reactants or one of the products needs to be a gas for pressure to be an issue. And that is essentially like changing concentration. And we'll talk more specifically about this in a minute. Changing the temperature, obviously, is going to disrupt the equilibrium. And then addition of a catalyst, which we talked about in kinetics. So depending on what the change is, we can shift the position of equilibrium towards the products to the right or towards the reactants to the left, or possibly have no effect at all. We're going to talk about all of those potential shifts. And what we're really interested in when we talk about shift to the right, shift to the left, is changes in the equilibrium constant, which is generally going to be Kc, but may also be written as Kp when we're talking about pressure, which is basically the gaseous version of concentration. I mean, you can have changes in concentration in gases as well, but changes in pressure gives you similar effects. Okay, so back to the Haber process. And you know, Fritz Haber, he was kind of a jerk, and he also, you know, the production of bountiful ammonia also led to wonderful things like explosives. So, you know, this isn't just happy, joy, green revolution fertilizer. But what he figured out was that because the reaction to produce ammonia involves a bunch of gases, and that he could selectively remove some of the gases from the reaction mixture, he was able to shift the equilibrium towards the products. He's able to find a number of ways to shift the equilibrium towards the products to produce more ammonia, as opposed to just throwing a bunch of things in the vessel, letting it go to equilibrium, and then just, you're done, right? He really wanted to find ways to push it so that he would be able to make more ammonia. And it wasn't just him. Obviously, there were a host of people working on this, but he's the one that gets the credit. So if we think about the Haber process in the context of Le Chatelier's principle, we can think about the various effects on this. So one of the things that Haber figured out is that if he could remove the ammonia from the mixture, then he would shift the equilibrium to the right towards the product. So as the ammonia is produced, it gets removed from the system, and the same amount of nitrogen and hydrogen will then react to replace what's been removed. It'll shift that equilibrium towards the right. And that has the effect, so by taking ammonia out, we've decreased the concentration of ammonia, and the system will react to increase the concentration of ammonia to make up for that decrease. So it will react by shifting towards the production of ammonia, minimizing the effect of the change. It's just a hallmark of how these reversible systems work. So removing a product will drive things towards the product side. And then also changing the pressure is going to have an effect. So thinking about something, a reaction, this is kind of hard to see, sorry. 2A gas is B gas. All right, so this is, A is our red dots here, B are the yellow dots. And at the beginning of the reaction, we've got twice as much A as we have B. Okay, we have 2 moles of A and 1 mole in the reactants and 1 mole of B in the products. If at this point we increase the pressure so that we crowd these gas molecules together, the system is going to react to try to relieve the pressure. And remember that pressure is in this system is dependent, in a gaseous system, is dependent on how many particles we have and the volume, right? So we increase the pressure by decreasing the volume. And the system is then going to react to move towards the products, because that will, this has less space, and we want to get the pressure back to something close to the original. And by shifting towards the products, where we only have 1 mole of gas in the products versus 2 in the reactants, we can decrease the amount of space that those gas particles take up, and therefore decrease the pressure. If we decrease the pressure of this initial reaction, and by increasing the volume, for example, then again, the system is going to try to make up for that to end up with a very similar amount of particles, or similar concentration of particles by, and make up for the decrease in